my collaborators or students.
Sorry.
So which are present here. So Juan Carlos, Caterina, Andrea, or Diego. So we just raise your hand and we should be able to help you. So the idea is to go a little bit step by step. I will show some of the features. So the idea behind MOAnalyzer was to quickly go through your output data of a DFT, because sometimes it's just a little bit overwhelming, and so you quickly can analyze and basically make decisions if your calculation is means something else, or if something is, or if it is correct, like to basically drive some conclusions from that, especially when comparing with experiment. So, so this was developed in 2010, and then after that year, I have made very little adaptations, but only this year I started to do some improvements again after the interest of Macon, which contact us and some others here at Slack. And so we plan to actually put some visualization of molecular orbitals, which is at the moment not possible. So hopefully you had access to this kind of like these direct links to the download materials. And I will try to do the presentation now. Okay. So I'm gonna present some of the features first that we can do, like a quick exploration of the tools. And then I'll use one that is not in the tutorials that I developed on the last part, just before just after, sorry, the original tutorial for the program. So I would like to explain a few things about this, the MOAnalyzer plot, to be able to compare directly with the experiment, which is quite useful. Sometimes you want to play a little bit with the broadening, with the shifts of energy, as well, what energy shift you will need to apply, and also the intensity scales and things like that you can use afterwards in the main MOAnalyzer to be able to interpret what transitions are behind a particular set of peaks, for example. And I go through a few examples as well of how to do several things regarding the interpretation of the spectrum. And so one of the things that is most convenient about the MOAnalyzer is how you can obtain the contributions to particular fragments of atomic orbitals into your molecular orbitals. So basically the percentages that based on a population analysis are present in the calculation. Something important is that you need to put the normal print in ORCA in order for the program to actually read through the information printed there. And also, it was originally we used to have this very standard, and at the moment of development, we didn't include the F orbitals. We are working to incorporate also F orbitals, which are important in many projects that involve organometallic structures. So we are working on that this year, in addition to the visualization of molecular orbitals. So one can obtain a table like this, which basically tells us the amount of for each fragment, for each molecular orbital, what the percentages of each fragment will be. So having a table like this is quite nice to know if your calculation is right or need some sort of improvement, or to get information directly for your calculation. And it also brings some molecular diagrams, like give you an idea. Perhaps not like it won't be the best, it won't be the last year for your publication, but you can start from there and build on. There are several publications where we have actually taken a figure like this and then improve it. I'll show you a few examples of that. And so for the interpretation of X-ray spectroscopy, the whole thing relies, because it's DFT calculations at the moment, but later we can incorporate some other initial methods. The MO picture is often adequate for this kind of interpretation, in the sense that, as we saw in the ghost talk, it's not always the case. More than often, we see many states as opposed to orbitals. But the first approximation, you can see the transitions to typical 3D5 low spin. We will see, for example, two transitions, and in a low spin 3D6, we will see only one peak. That's exactly what we see, for example, in the iron TPP B similar complex, no? As a first approximation. So the time-dependent DFT calculation is a good start for that. And another example is X-ray emission spectroscopy, the valence to core region, where you can almost interpret your spectra with molecular orbitals. I guess it's just depending on what the electron that is making the transition is subject to the surroundings, how much is changing while the transition is happening. So we will assume that approach. So this is an example of the valence to core, how fragmenting the molecules. So we will go in detail in this for this example, because we have the output for this in the tutorials. So let's just start with this example again. Just try to reproduce the table there. And I mentioned before that it is better to use the MATLAB version. It's like there is issues with visualization and the MATLAB. Okay. So basically, once you have loaded the, okay. Once you have loaded the library of functions for MATLAB, all you have to do is to type in the main command window, and then this will appear. And then we can just explore first one of our examples. I will go with this one, for example. So this calculation is for iron, TPP, bicimidazole. It's a single point calculation. And it contains, so it's basically reading everything that is in the file, orbitals, geometry, oops. Still reading, yeah. And then you will see your molecule. Depending on the version that you download, one of the latest improvements was the visualization of the molecule. So first, we need to fragment our molecule. So we need to decide which contributions will go with each fragment. So for example, here we can put every atom in the TPP on the same fragment, all the orbitals contributing to this or being part of this fragment can be put together. Then the iron in another fragment, and then the two bicimidazoles in another fragment. So we decide the number of fragments here. For example, we can decide to have 3. And then sometimes in the structure, in the optimized structure, the crystal structure that you obtain, not necessarily goes into a particular order. Sometimes you have to look for which atom belongs to which fragment. So for example, here is convenient, is the first one is iron. And so it will highlight which atom you are selecting. And then you decide which atom to send to each fragment. For example, here we can put the iron in the first one. And then once you click in these buttons, then you will add the atom to this fragment. You can also type it directly if you know the ranges, for example. So the next atom is a carbon in the TPP. And so we'll put it in the second one. Then you can keep adding all the atoms. So sometimes it so happens that depending on where you get the structure from, like randomly in a different position completely. So, but here is, it seems like all the way to where the first nitrogen, well, maybe this one is also part of the TPP. So all these atoms are part of the TPP all the way to 77. So this hydrogen is still part of the TPP. So we can put here a range 5 to 77. And then starting on 78 is already the imidazoles. So we put in the third fragment. And so all the way to the end, 95. So we can put another range. 95. And so with that, we can also decide for each element which orbitals to look at. For example, the iron would be interesting to look at S, P, and D. because the valence orbitals are actually 3D, 4s, and 4p. So it will make sense to look at the contributions. And then also this file detects that there is some XCS and XAS calculation. So Orca has this very nice thing of calculating from a particular orbital acceptor or donor, in this case the 1s, all the basically single particle excitations. So for example, you can calculate the full XAS from the 1s to all the unoccupied molecular orbital, which in this case is total of orbitals is 1,667. It doesn't mean that it's going to be doing a good job, but you will be surprised that oftentimes it matches the time-dependent DFT dots for, let's say, a number of routes. Let's say you do 40 routes or 50 routes, and then you get exactly the same answer with the single particle model, which means that the transitions are actually not interacting with each other. And so you save a lot of time, because if you know that time-dependent DFT is doing a good job, I mean, it's kind of reproducing or mapping the XAS, then you do a full XAS and with the single point calculation, and then finish more quickly and get more transitions. But it's only in certain cases when this will work. So we should be able to print a table. I'll show you some pictures. For now, I will remove the spectroscopy information. And we shouldn't, I will remove some of the orbitals here, not to print the 1,000, but to print, let's say, the first 200 or so. Then there is this option here to look for the ones that are important to you. For example, here is carbon, at least to print all the orbitals that contain at least 5% of carbon, let's say. But for now, we will print all of them and see what happens. So it prints the alpha and the beta orbitals, the alpha of orbitals, the beta orbitals. So it starts to print these tables. I'll stop there. Right, so because it's too many. And then let's go to the first page to try to see if they kind of make sense. So the very first orbital is 0 alpha. So if you see all the energies in green, and in particular, this is important when you are close to the valence orbitals. If you see them green, it's a good calculation, the ones that are relevant, the unoccupied particularly. If it is like positive, because the green means that they are negative, and if they are positive, they start to become like, it's probably not a good calculation because they should be positive, even if they are unoccupied. The occupant, so that's how nice if it is probably a good calculation or not. And then this color is the occupancy. They are highlights if they are occupied. So you could see here that this must be the 1s, the 0 alpha. Then this one is the 2s, the 2p. It's practically atomic orbitals. They don't mix with anything. They are 2D in part of the core, basically. And then you have the nitrogens. So this is the 1s of the nitrogens belonging to the imidazole, because the fragment number 3 is the imidazole, this is the porphyrin. Then you have the 1s or some of the 1s of the nitrogens also from the porphyrin 3, so it's the 4 of them. And then the 1s of carbons, which is more of carbon. So it's basically what is printed in the first page. will be convenient to have it all in the same page, which you can do using this tool, create ASCII. So it will create ASCII with all the information all at once, and then you can open, for example, in Excel and have the same highlight of the, because you can also program in Excel the coding of the color coding. Because look at what's happening in the second page. So here is the 3x of the iron. This is the 3p. Starting in orbital 67, that's where the balance starts. Because you start to see a lot of shades of gray. You can decide the color as well. So either could be black, blue, or red. I mean the shading of this part. This is not the most important part, but still, I mean, this helps you focus in the important contributors in a particular molecular orbital. So what if we want to focus, so you see like how many pages it prints this thing. But what if we want to focus in the most interesting ones? I don't know if there is any questions or if anybody is following step by step.
My orbitals won't load. It just says loading orbitals.
Get stuck. And this is the MATLAB version, or?
That's the MATLAB version.
Perhaps there is an error in the main MATLAB. There might be an error like this. I mean, this one is because I stopped the printing, right? At some point, I stopped printing the pages. So I wonder if there is an error in your command window that you can see.
Yeah, it says error in fill orbitals.
Which version? So that was the MATLAB version, and download from here. And then the other thing that I should mention, that this should be on the path. Like everything has to be on the folder of that you use for the MOAnalyzer. But anyway, when it opens, should put everything on the path. So, but it still doesn't load it like this. And
Like that, I'll keep trying.
Are you using I made a mistake too at the beginning. Are you using the FETPP_XAS out? Okay. Just because there's another FETPP one.
oh,
I tried to load that one first. It didn't work.
oh, there is one that doesn't work.
Why? I mean, maybe it works. I don't know. It's the iron 3 TPP P_isomidazole.
You mean from the examples?
Yeah, from the example list. Yeah.
Mm.
I probably did something wrong.
So let's go again to the main. So it should be this first example. And then this one doesn't work.
I only tried that one, but yeah.
I can think of top of my head why it shouldn't load. And then these examples are available from the tutorial here. Examples and tutorial. And so instead of printing the whole table, did it work, the loading or no?
I'm moving things into a different tab.
Maybe you can help. And so let's say we select this option of the orbital is 5% of iron. Say it goes a lot of time. It's just a short list. And so here again is the 1x, here is the 2p, 3s, 3p, and then you see the most relevant orbitals that contain iron, molecular orbitals that contain iron. So this list is too short, I realize, because we still missing the unoccupied. So let's print another one. Because this list is goes to 200, but let's go to 300. So this is a nicer one, because it contains also the unoccupied. And so we could see here that here is where the 3D orbitals will be located. I should mention that the geometry used is not fully optimized. So that's why it's very weird. Not completely. So we could see, and this doesn't contain the natural orbitals option, which is a cleaner version of the. So this one is just a raw calculation, single point calculation on a not exactly optimized geometry. But you could see that one of the things where you can realize it's still not optimized is that you will see strange things like the ordering of the orbitals or having not exactly matching the what you will expect for a low spin configuration. But another thing that you could use this for is to spot where your 4P orbitals will probably be. And the contents of the 4P orbitals mixing with the 3D if they are present, for example. Sometimes you, so the kind of spectra that was presented today included some 4P mixing, so sometimes you can spot also the 4P 3D mixing of the orbitals. So I don't know if anyone else is.
Yeah, so for example, here, are you kind of saying that like an orbital 232, we can see some P character in the ion, you're saying that's where the 4P
Right.
points are here?
Or at least you use orbitals, molecular orbitals in the unoccupied, which are mostly concentrated in the porphyry or the imidazole that contains 4P character.
Okay.
And those you will see it in, for example, in an X-ray spectrum, just so you will see it probably below the edge. So, yeah, it will be hard to see, right? Or sometimes if there is enough structure, like for example, in this one. in this spectra here. So you could also see these contributions to the IMS, right? Or the charge transfer transition, where you could also see this.
Okay.
So for example, taking note of the 3D orbitals, the one that has the largest contribution. So let's say 204, 205, 207, and then these two to bring a molecular diagram, let's say. Then we can also take, so this is for the alpha. And then for the beta, we can also take, let's say 205, 206, and then these three to print it in a molecular diagram. I should probably do it for, if there is anybody following this? Anybody else? Or?
I got my file to load, that's as far as I got.
Oh,
Yeah. Huh?
I just, for the, printing out just the important ones, could you go over how you did that again with the, like?
Sure.
fragment threshold?
yes.
Yeah.
To print the important ones, we will have to click here, the fragment threshold, and then we put the element that we are interested in and the percentage.
What does percentage refer to?
So that will be the limit, the low limit of
Oh,
let's say, at least having 5% of iron, let's say.
Oh, okay.
And so if you click this one, has this option, then it will print, for example, 0 to 300 with at least 5% of iron. And as I said, even if you, I mean, you can have the full list here, which is very convenient, then open software like Excel and use nice to put in a different Excel. So everything that you see in this table, you can also visualize in Excel and put the color back in some code as well, instead of having several. But if you do it here quickly, this function is very nice because you highlight only the one that contains a particular element that you are looking. Initially, we also don't put this information just to have a more simplified version of the table, because once we put the spectroscopy, this calculation contains some XCS. Particularly interesting will be the balance to go here, and then it also contains the XAS, which will be interesting for the, let's say, the KH. One next to all the empty molecular orbitals. But that will come like more handy in the second part, in the graphical analysis. Now I prefer to focus more on the for this part without the spectroscopy, and then we will go back and actually highlight some of it. So it continued not working. And so the error, so we'll probably try to, so we'll have another break and I'll try to fix it in the break.
What do you do? It might have worked.
Oh, it worked already? Excellent.
Maybe.
So when it works, you will see this structure finally.
Yeah.
So you reach to that point?
Yeah.
Excellent. So once you reach that point, then you fragment by creating like 3 fragments, one for iron, one for the port fitting ring, and one for the two imidazole ligands. And so you have this atom selector that allows you to go through each atom to see where they belong to. Or you can simply type these numbers. I mean, if you more or less know the range, sometimes oneself creates in some software like the Delgado or something like the original geometry, right? Like to optimize. So you already know what the order you were using when you create your figure. But sometimes it's from crystallography, and sometimes in crystallography the ordering is very strange. So that's what the atom selector becomes very handy, because then you can assign quickly through it, or not so quickly if the molecule is too large, but anyway, it's a tool used for helping with that classification of atoms into different fragments. So in this case, we know that the iron is 1, and then from 2 to 7 to 77. So in MATLAB, we put the range to these charts. And it's all atoms belonging to the TPP. And then for the imidazoles, 78 to 95, it's all atoms belonging to the imidazoles. So that's the basic construction of, let's say, the three fragments, the basic fragmentation. And then we say that at the moment we don't want these options to be on. By the way, it has also the possibility of analyzing block symmetry solutions. You're interested in that. That's one of the things, one of the last things I did in 2010. But now we are going to try to do more stuff. And so we were focusing also in the orbital region from 0 to 300 that could be most relevant. And then this option of the threshold allows quickly the most important molecular orbitals that contains iron. Especially we are connecting these to spectroscopy, would be very relevant. And so, oh, this is actually the room. Close this one. And then create again the alpha B. So we could see starting from here, all of these are molecular orbitals. So you could see also if there is any need. So you see a lot of 3D characterization between the highest occupied and the lowest occupied. But then you don't see any 40 mix in this case. I think there should be a little bit of 40 mixing in the real. As I said, this calculation I did it from a geometry that is not necessarily well optimized at the moment. So it's kind of idealistic of where it should be, but in reality there should be more 40 mixing. And we will see it as soon as we see an asymmetry between the axial impedance, so we will see more, or deviation from the plane of the EPP as well. See that. Anyway, so that's what we have in this calculation. It is what it is. And so going back to the main interface to try to fill the information for the graphical analysis, where we can put here the molecular orbitals that we identified as interesting, for example, the 3Ds. And so this is again the graphical analysis. But perhaps I should ask if whoever is following this tutorial were able to produce the tables or not. Good. So in the graphical parts, then we can put, for example, the 3D orbitals that we identify the alpha, first the alpha and then the beta. Oops. Sometimes when there is an issue with the screens, MATLAB crashes. In that when my extension on the other additional screen fails. But it has survived so far. So we say that it was 204, 205. Oh, yes.
So when we are making the tables for the iron, why is there a different number of orbitals for alpha and beta?
Oh, yeah. What happens is that the alpha ones, so up to certain level, let's say to the atomic one, they should be exactly the same, matching exactly the same. Which in this case, otherwise we have like a very big problem with our calculation. So in this case is, I think it's 67, the very last one, or 66 and 66. So those are the 1s, 2s, 2p, 3s, 3p. And so those are atomic. But afterwards, in particular, where the spin polarization begins, like the alpha and beta starts to go in different energies because of the spin polarization, then you will see a discrepancy between the which one is which. So you can see a very different energies and very different percentages of metal and ligands. You could even see orbitals that have different identity. So not necessarily the same orbital, especially in this region, will be iron based than in the other region, but that's because essentially spin polarization. And so I wouldn't expect this to be different for two different in this region. Just for the first molecular orbitals, I wouldn't expect that to be significantly different, but they will start to differ more as we go closer to the LUMO and HOMO region. That's where we will see. And this calculation, I mean, for several reasons, I know is really bad. It's based on a geometry that is not properly. So if it is properly optimized geometry, I wouldn't expect to be, especially in most cases, these numbers to differ at all from these ones, unless you are in this region of the 3D, 4S, and 4P orbit. Any more questions regarding the tables? So what we were trying to do next is to fill out the molecular orbitals that we associate with, let's go first to the alpha. And for that, what I normally do is to write down a piece of paper which ones are interesting. But here we can see, for example, let's put all these with high percentage of 3D character. So 204, 205, then these three, 207, 211, 12, and then for the beta ones, this one. Basically these five with the highest percentages. That's another, I mean, they should be together, but as you could see here, there is some that is probably pi back bonding orbitals, kind of like in between the 5D shell. It's possible that to happen, but in this case, it's because it's geometry that is not optimized. So 205, 206. The highest one. And then 208, 211, and 212. And then we can print a molecular orbital diagram with this. So we could see a little bit of the spin polarization here. So how, for example, if it is, whenever it's high spin, this one goes all the way up here when it's high spin. And first we fill this orbital, and then later the beta orbital. In a low spin situation, we don't have too much spin polarization, so they are almost on the same level. And so we see the alpha ones here in the P2G and the E, so there will be an empty spot right there. So I don't know if you were able to reproduce this. So what this means, the levels of this has to be calculated from the entire population of molecular orbitals. So one calculates the average energy of what you will put in a molecular orbital. So what it is, for example, the 3D. So what we are trying to find with this is the average energy of this, of the 4S, of the 4P. And this is just a very rough estimate based on the energies and the composition of the molecular orbitals is where we get this from. So kind of like the average energy. So we can do a much better, so you could see here how the 4P is below the 4S. But to improve this kind of like calculation is not very important calculation because it's just an estimate of the average before interaction of all the atoms, like when the complex is formed. But you know, like if you want to use this as a template to later put your molecular orbitals, which I have said that we have done in the past. So we put a number here to, rather than obtaining the energy, the average energy, we obtain like a higher momentum of the energy. So what it is that you form molecular orbitals. So the unoccupied go higher in energy than the occupied ones after they interact with each other. And so the energy is kind of skewed towards the bonding part, the average. So if we use the higher momentum, then we have a better estimate of the energies of the different fragments. So we use a number 5 there. Usually 3 to 5 is a good number. And then we have a better estimate for the 3D, for the 4P and the 4X. So this is another indicative that this is a wrong calculation. I mean, this is not based on an optimized geometry, as I have said. Because at this level, with this number, this one should be up higher than 4x, which is low. And so this will be, for example, the nitrogen 2p or fragment number 3, which is the imidazole, and then the carbon P and the carbon S of the carbon P, sorry, from the fragment number 2 and number 3. We can, using, I mean, this is just MATLAB thing. So we can change the names of this, so this is the, make it nicer, properly labeled, and move it around. So instead, you can use this as a template or not. Just get a quick analysis and then you do your own figure with that. And then this one we say it was the nitrogen of the 2p.
How are you editing the figure?
To edit the figure, we go into this, and then you select the object,
Oh, okay. Thank you.
and then you can just type there. Also highlights the number of the orbital that you can also put on. For example, this is a 3D, let's say x squared minus y squared. I mean, you can put that, sorry. X squared. So it's in LaTeX format. And then
Where do you see the geometry of the orbital?
this is not printed. This is something that will come after we were able to visualize the molecular orbital, which is coming soon in the next months. So this is a recent upgrade. Be able to print the orbitals here, which is which will be similar to chemical. But then that will be more easy to actually label. Here is what you an example. Orca actually doesn't, I mean, it tells you that information in the printing of the, but we decided to condense the D character rather than to separate it because it will be like 2 long tables. So it was a different purpose. But then I'm recently thinking in connection to the visualizing molecular orbitals that it will be a good option to have like either condensed or not condensed pure orbitals. It makes more sense in connection to natural orbitals like this option of doing the NTOs rather than having this. I mean, in these calculations, I didn't put these options, so you will have a lot of mixing that is not like a textbook molecular. So this labeling makes even less sense in this kind of calculations than in the other type of calculation. So, were you able to actually obtain this diagram more or less? Okay. And so another thing that can be done is what if we want to compare to experiment, right? Like our calculation to experiment. And this tool, I've been told that is very useful even for very heavy calculations that you can do in Orca. And sometimes the outputs are like 1 gigabyte or so of information. And all you want is just the transition somehow, this very large output. And so for that, just for that purpose, this tool could be very useful, the plotter, which you can access in 2 ways. You can access clicking in this button, or alternatively, you can access through the here just type in MOAnalyzer and then plotter. I'll show it this way because it's more illustrative for that. So importantly, so it's the MO and then capital A, and then the P is also capital. Click enter. Then you get this interface for the transitions. Later we will see first, so this is kind of like an optimization of the calculation to the experiment. And then once you get your parameters, we can also use these parameters to improve the information of our tables and the molecular orbital diagrams that we just produced. So let's first bring the one experiment here, experimental data here, which will be this one. So it's iron 3 TPP bcimidazole. So then let's select like a good range for the pre-edge. Let's say 7120. And then also on the Y, perhaps going to only 0.05, something like that. So again, it's 7108 and 7120 on the X, and then the Y 0 to 0.05. What is convenient to do here is to freeze this scale because it's the experimental scale. So when we load the calculation, it doesn't go to a different region because as Gus pointed out in his talk, the calculation is in a very different region of energy. So we always need to shift it to experiment. So if we actually don't do that, so this scale will go towards, once we load the calculation, we go to that region. It's fine, but it's annoying because then we have to put this one back to where the experiment is. If you are just comparing calculations, a series of calculations, you can also do that. Then it's more convenient to go to the other region actually. But if not, this is very useful. And so now we load the calculation, let's say the same calculation as we did before, the XAF, the iron TPP XAF. So we will see that it's not a very good calculation because it doesn't match too nicely the experiment. And then it asks us what kind of spectra you want to plot in here. So we say XAS in this case, because it also contains emission in this particular case. So we see this red line here. We are completely out of range. Yeah.
For the spin stick option, why would you want to plot just alpha or beta or none?
Oh, yeah. Sometimes you want to highlight in your spectra which transition they might be only to the alpha and which ones are to the beta. So which transitions goes to. And this is particularly important in low speed because then sometimes you have less option. For example, it depends on the complex, I should say. Because for example, if it is a high spin iron 3 complex, then you will have, so you know that is only beta. But let's say you have something more interesting where you have a very different amount of alpha and beta, and you want to highlight here. So you only load the alpha, for example, and then you can only load the beta afterwards and try to optimize everything and see what what contributions comes to the alpha and what contributions comes to the beta. So that could be handy to do that. If you don't put any, then you just click none, and then it plots everything. So we don't see anything here because we are not in the energy region of the calculation appears. So we need to bring it up and to the same scale because the calculation, the oscillator strengths are in the order of the -3, -4, sometimes -5. So we need to scale it up with this tool. And the energy shift here, I kind of already know that is around 56. So we still don't see anything because it needs to increase this number by a lot. So see now we see the calculation. I think we were not too bad with the 1000. And then we see a lot of transitions here. This is because it's the kind of single particle calculation that goes from the 1s to every single of the empty molecular orbitals. So that means from the lumen all the way to 1,600 molecular orbitals. So here it only modulates it creates this band from the sticks, from the calculation. From the first transition to the 200 transition, but you can go all the way to 1,000 transition. So it's just by the default is maximum 200. For example, in a time-dependent DFT, it's common that you only explore like the first 50 roots or so. So it will show 1 to 50. But if it is more available than 200, it has like this limit. I mean, you can go higher, but by default, it will appear like 200. So, but let's put 50, which is normally what you have in a time-dependent DFT calculation. So now it doesn't go like crazy like this because it starts to become more intense after. The sticks will still be there. You can remove the sticks if you want. But the broadening is not so good. So let's change first this number to, let's say, 5,000. So it's again 1 to the first transition to the 50 transition. We are applying an energy of 56 electron volts to bring the calculation in direct comparison to the experiment. Very broad. We don't like it. So I'll explain the broadening. So let's do first single broadening. Yeah, simple broadening. So you see, it is using a 0.1 width that has the maximum. So unfortunately, Hertz doesn't do as good as this, but I mean, it's still quite good, but we need to increase the width a little bit. Let's say it's 0.15, 0.2 over there. So it must be around 0.5, which is quite good. So you could see, I mean, still we need to increase the intensity a little more. It's not a very good calculation. So we saw many very nice calculations today, but this is a very bad calculation. And sometimes this level of calculation is also presented as good calculations, so it's all relative. So one could argue that this should be here somewhere. Right? Let's dig it with these two, something like that. Surprisingly, let's exactly in the same geometry, let's load the time-dependent DFT calculation. So exactly in the same. So it's the second one that is shown here. Oh, actually, where did it? Oh, I clicked on the wrong button, so it will be here. So it will be this calculation here. And so the type of calculation we write, so it will be time-dependent DFT. And so they are almost agreeing. And it's just a factor of different scaling factors. To see them together, we click on stack. Perhaps it's convenient to go to a lower intensity. They are almost the same. Very often you will see this, that the time-dependent DFT calculation is exactly the same as the single particle mode calculation. And if this is the case, you save a lot of time. I need to see them more, so you can remove the sticks from both. They only don't match the intensity because the XAS single particle is done with a very weird normalization. So it is normalized with the highest intensity in ORCA, and that's why they don't match in the scaling factor. But that's the only difference. The rest is practically the same. Transitions calculated one way or another. Let's say you want to save this, right? So all you have to do, so you have two options. So if you like to have this in MATLAB, so you just click here on doc. Oops. Hopefully that doesn't kill my thing. There it is. So it creates its own figure, which you can keep editing if you like remove some parts. And then you can save this as a figure, but I will think that the most useful feature for most people will be to actually export as an ASCII files of every single plot. So it will be the three with these names. Well, let's actually do that. Example. So it creates three files actually with this name example. So it has, so these files has a name and a last name. So the name is example, the last name is exactly the name of the calculation that we loaded for the experiment. And so these files are just X and Y. So we can plot it in our favorite program rather than in the figure of MATLAB. So, but as I said, if you like MATLAB and you want to continue with this figure, you can also click on top. You click here on doc, it will print this in its own figure, and then you can edit it actually, save it as a figure. you know, ready to go. Publication. So, yeah, this is very useful because you can actually obtain these parameters. And with these parameters, you can actually even do it by hand yourself, right? Like this is like a quick comparison between experiment and theory, especially handy when the outputs of the calculation is too big, way too big. So it will do the search for you, quickly get the transitions and
Is the TDDFT calculation has a way lower range, or is it just the grid? Like if you show.
right, right. So let's put the sticks back. So it has a photo here, but that's because in the calculation, I only put the first 50 transitions. The more, I mean, I always have the issue with the computational resources, sorry. But if you don't have an issue with that, then you can put like way more roots. So the thing is that time-dependent DFT calculation is a little bit expensive if you put a very large number of roots, because then it has to deal with the mixing of transitions. And if it is too large, then computational times would be prohibited. However, look at this overlay almost exactly as the single particle. The single particle is so inexpensive that it's more convenient to actually have. Like
The rest of
everything.
the edge.
So let's actually look at how far it goes. I mean, it doesn't mean that it's doing a good job in that region. You're saying that it calculates like, look at all these lines here. So technically, I mean, we can, so because sometimes this is actually a good point. Sometimes you see structure here too. Some structure here, which is, for example, transitions from the metal to ligands, which will be also interesting to include in a time-dependent DFT calculation, right? And there are protocols, for example, when you don't get exactly, well, I'll actually go to a lower range. Sometimes, so let's say this one is a LMCT transition or the other way around, an MLCT transition, and you don't get it right. You often actually are not going to get it right with time-dependent DFT. But what you do is to follow a protocol of mixing different Hartree-Fock quantities to see if actually you, with one of these amount of correlation and exchange, you get it right. So you do a systematic variation of that until you get it right. If that's kind of like the interest to find out like a percentage for Hartree-Fock that will actually represent well your experiment. But perhaps the first will be to run a single point calculation to get as far as you could go. That will allow you to see how many roots, to decide how many roots you will need to include in your time-dependent DFT in order for you to see the MLCT or the LMCT transition. So since it is inexpensive, so it is convenient to do that first, and then you do the time-dependent DFT. Following also the protocols to identify MLCT or LMCT as well. The thing is that, for example, the transitions to So let's say we have here some empty molecular orbitals which are 5 star. And once you excite an electron to the metal or excite to the 5 star, which are mostly ligand. So once we do this excitation, the entire structure of the metal will go down because we are removing one core electron. And the ligand, which perhaps like the ordering of the ligand, has a different behavior once we create a hole in the metal. So it's like less subject to this kind of relaxation effect. So very often we don't get right the LMCT or the MLCT for that reason. So the different, and so this mixing with the Hartree-Fock correlation and exchange will allow us to get a better answer to that. But as Gus was pointing out before, there are limitations to time-dependent DFT. And so we need to get as many experimental, so to fit the most experiments with the same model as possible, right? To decide. So is there any more questions regarding this MOAnalyzer plotter?
For the Hartree-Fock exchange, you're gonna go through and systematically vary it. You're talking about doing that, I think it's the SCAL HFX keyword, right? And you're talking about actually doing that in order. Calculation, right? Yeah. Is it important to, like, say if you're gonna do a TD-DFT calculation, is it important to do that at the level, like, should you do that, should you re-optimize your structure with that level of exchange, or
That's a good point.
only do the TD-DFT with that level of exchange? It seems like you probably want to re-optimize the structure also.
Yeah.
Well, you also on top of that do both the re-optimization and the calculation, then you have two reasons why you might see a change.
Yeah.
Like if you keep the same structure and you just change your functional,
Yeah.
then you know that your change will come from the change of functional. But if you also change the geometry, because for example, going from BP86 to BP3, for example,
Right, yeah.
you might get some bonds that are going to get shorter or longer. So then you don't know if things are shifting because of that or because it's
Right, yeah, it's just a time and computational resources issue. Makes the optimizations expensive.
Mixing back to FX again, right?
Yeah.
Yeah, that's a good point. I will personally go with the approach of what Gus is saying. Yeah. But I mean, I've seen also the other approach, but I will personally go with the approach is saying.
just not a lot of parameters changing. It's like
Yeah.
And so let's say we have already our shifting parameters, right? So we can go back to our table, for example, and put the XAS back here. And then go to the graphical part. And then here where it says absorption, to put the shift that we found, 56. And then here there is this field here that it says molecular orbitals that are the acceptor or donor. And then you know that for this calculation it is actually 0. So the very first orbital, which is the 0 orbital, is the one that is actually donating the electron for the transitions to happen. So sometimes we have more than one, and so we put all of them there to give us the information in the tables and the molecular orbital diagrams as well as a projection. So let's do first I don't want to go too fast here. So again, I put a shift of 56, which we found when comparing the calculation to the series. And also we put the donor orbital, which will be the 0 orbital, which is the one of the item. And then with that information, we can actually obtain by clicking and close this one. It's here. So here, let's create a table with this new columns of XAS. Oops. Nothing printed here. But that's because I don't know why it didn't print anything, but normally it shows here.
I think it'll print if you select the XES instead of the XAS.
Oh,
So I noticed in the output file it had the XES
right.
there.
Yeah. Actually, the key for accessing single particle in Orca is XES as well. It might be. Oh, there it is. Oh, but it's printing the X-ray emission spectroscopy, but not the X-ray absorption spectroscopy. So let's see if we print both, if it works. So there might be a bug there. Same thing. So there should be a similar thing to here. So here is for the emission part, all the lines that are coming back to the one end, which we haven't discussed in detail, but it tells you basically the transition, the energy of the transition. There is a shift on energy, it applies that shift already. And you can correlate the transition to a particular molecular orbital. It's supposed to be doing the same for the XAS. Let's try with the time-dependent DFT calculation. I know it works. For that, there must be a bug here, which I will correct. So originally we used for two calculations, the time-dependent DFT and the XES in the balance to core. I forgot to. Maybe I'll show with the last example because we don't have too much left, right? So the last example will be, I wanted to show also the nitrogen KH because the nitrogen KH, you can get away with a single particle model. I strongly recommend that, use the single particle model. So actually, I should ask you, would you be more interested in focusing on the example of the nitrogen KH or the balance to core? Nitrogen KH. Okay, let's go for that one. So the nice thing about ligand KH is that you can get away with calculating just with the XES, both XES command on Orca. You can calculate all the XAS of the ligand KH with almost no errors in the same. I mean, you can get the same solution as time-dependent DFT is what I'm trying to say. Because, as I said, when you create like a hole, in this case, you will create the nitrogen 1x. So the relaxation of the ligands, so the ligands are already lower in energy than the metal. So if you create a hole there, the ordering of the ligand orbitals will remain lower than the metal. And that means that if you try to do the angular calculation, you will practically will get always the same answer. So which means that you run an XCS calculation particle in order, you get all the transitions to the empty molecular orbitals. And that's it. You get like the full structure as very similar to what Gus was showing with hydrogen DFT for the oxygen KH, but with the single particle model, which saves a lot of time. And so here we have a molecule with of iron with 2 isothiocyanates, and we have 5. So in the equatorial, we have a ligand with 5 nitrogen. So it's very rich in nitrogen KH. So we can actually take a look to the calculation with the plotter, or we can just do it directly here. So I'll show you this feature as well. So we need to first fragment the molecule again. So the first one will be iron. Then from 2 to atom number 2. Oh, sorry, this is for fragments. Atom number 2, 2, 3, 4, 5, 6, 7, all the way to 7 will be isothiocyanate. And then from 8 all the way to 50 will be the equatorial ligand. 8 to 50. This is just to identify the nitrogens of each fragment. So that's kind of. We can even put like a 4. Actually, it would be good in this case to put a 4th fragment, aiming to identify this nitrogen here, which is not directly linked to iron, used to as isolated as well. But okay, let's see if we can find it quickly. So good thing is that we don't have so many nitrogens. That's not it. Oops. That's 29. So we can write down 29 there. And so it's 8 to 28. And then the other range will be 30 to 50. The rest of the atoms there. So we are just isolating this particular nitrogen, just to identify the molecular orbitals that could be interesting for this nitrogen from the perspective of this nitrogen. And then we have everything kind of classified this way. So first we remove this, and then we create our table. This is, we are actually the ones who contains only iron. I didn't, so let's print the ones that contain nitrogen, which are relevant to the KH. Nitrogen KH. So nitrogen, at least 5% or so. Maybe we can be more strict in the threshold, but it's not too bad. Still a lot of nitrogen. So here there is several possible donors here. See, so these ones are the ones nitrogen from the equatorial but directly linked to the iron. And then there is this one, which is supposedly not linked, so this one should also be a donor. And there is the nitrogen of the isothiocyanate. So all of these can participate. So we just need to take note of this particular donor orbitals, which is the number 7, number 10, and then for the isothiocyanate is 11 and 12, and the nitrogen that is far away is also number 15. Then let's do a molecular orbital diagram. Actually, let's identify where the important, not important, but let's put at least the MOAnalyzer, these two. So we go to the graphical and then we put 112 and 113. Used to have at least 2 molecular orbitals. Otherwise, we cannot print. So I'm surprised it hasn't crashed. Yeah. So here is like some projections that we can do. And then we identify it was actually from 7, 8, 9, and 10. It was from the nitrogens that are directly linked to the iron. So we can actually create the spectrum that how it will look like from these particular orbitals. So we select XAS, and then we create a MOAnalyzer. Oops. And as you were saying, maybe, let's see if it works like this. Now we create something. But that's actually the X-ray emission. So this is the balance score, what is plotting here because it's from the occupied part. It's just at the moment there is a bulk here with the XAS. It seems. Which is not working for the, because we don't see any XAS at all. We'll see it in the plotter though. But I like this tool that you can decide from which particular nitrogen, just that is not, I did something wrong in the last upgrade, and then I cannot plot XAS anymore. The other nitrogens were 7, 2. So this is the donor orbitals. So that was 10, 11, 12, and 13, I think. All the way to 13. Let's see. No, still no. Or maybe it's there, just that we don't see that many. Perhaps I have, so actually it's there. Just need to put less orbitals. Let's put 200. And less broadening as well. That will help as well. The moment is, so there is this shift that is for iron. Let's put a width of 0.1. No, still there. I mean, there seems to be like some tail of something. It's I put artificially like a very high orbital. Oh, finally we see something.
What was it that you?
Sorry?
What was it that you changed to get that to show up?
Oh, I put like a, so this is close to the homolumuga. I just because I did, so this is proper, if you bring in your table properly and identify which molecular orbitals, especially from the empty ones, are rich in nitrogen that you would like to explore more, then we create a demo diagram with these orbitals. And then it actually can project from this orbital you can project. So let's actually identify those. Something that is interesting other than these two. For example, in this table. Let's say we are interested in one that contains some percentage of this nitrogen. Does it look like? Occupied, so this will appear in the valence score, but not in this region. There is nothing with this percentage. But let's say we focus on the other nitrogens of the 4 nitrogens that are in this equatorial ligand. So these two could be very interesting, 120 and 121. Put these ones on 120, 121. So we could either add lines to the figure and add the projections of this. So this little thing here is the transitions to those particular molecular orbitals. Projection into the total spectrum of everything. So that's the projection. Or we can create a molecular orbital diagram that is focused on the transitions to this, which appear in this. There is a shift. Let's see what shift do I have. I have a shift of 0, but since the donor orbital actually has so it's not from 0 to something, it's from 7 to something. So it's that difference in energy doesn't match the scale of energy of the orbitals. But these two transitions to these two particular ones is this projection here. These cannot contribute because they are occupied. So it's transitions to this. So you can put all your interest, let's say you put all your interesting orbitals in there, the ones that contain nitrogen, and then it will plot the contributions to those. Also, the nitrogen KH is broader, so perhaps this will make more sense. Like this, right? Let's try to find some other orbital that could be interesting, higher energy. So at the moment, I will focus on these two, but we can also put this that contains significant nitrogen here, which will be 20 to 25. And ideally, we should put also the same in the K beta. Sorry, in the beta orbitals, 120 to 125. That's coming from all the equatorial ligands. 120, 125. So you could see that this second big peak so all these orbitals, so these are actually the nitrogen that is not interacting with iron. But these guys here that contain are from the nitrogen that are interacting with iron, contribute with this second peak here. To the spectrum. We can also identify the nitrogens that are interacting with the, let's say, isothiocyanate, which would be, well, actually, I was putting the wrong ones. Those ones are the isothiocyanate, and then the ones from the equatorial ligands are those. So that will be the first peak, probably, most likely. So it will be 116 to, let's say, 121. So we can add more lines to this figure by putting also the projections to that. 120, 116 to 119. And the same for the data. And then we just click add lines to figure. And then it creates another projection. It doesn't print the orbitals, but it prints the contribution into the nitrogen KH of these particular orbitals, which now are coming from the nitrogen on the equatorial ligand that are interacting with the iron. And the previously, this one, I made a mistake. This is coming from the second fragment, which is from the nitrogens in the isothiocyanate interacting with iron. So you start to decompose a little bit and that can be also done from the alpha and beta, so only the alpha contribution or the beta contribution, which could be quite useful to do. You can also do that in the plotter, although you cannot decompose the spectra with different molecular orbitals, but you can have the full spectra kind of like aligned to your experiment. So this goes along the lines of the other example. This figure here for the valence to core, where we were trying to identify a signature of a single carbon in a cluster. So we identify the highest contribution of that carbon to the molecular orbital, and then project in that way what will be the, so this shoulder here in the valence to core is due to that carbon in the middle, which was essential to have this signature to reveal the atom in the FIMOCO as well. That actually was carbide and not nitride or oxide, for example. But this was done exactly this way. There are a lot more examples. I just realized that we run out of time. Perhaps I was too quick in the last example. I apologize for that. But there are, the good news is that actually these examples can be also explored in the tutorial. So there is a tutorial. And my understanding is that Macon, for example, that's where he learned the MOAnalyzer from. So it goes through all the stuff that we were discussing today, perhaps more detail. And it shows the example of spectroscopy as well, how to do the spectroscopy. So this is also available in the materials that were included in the tutorial. So I don't know if there is any more, like one last comment or question. Thank you.
We're excited about these updates. Yeah, very good.
There will be more interesting with the, once the MO pictures are also available.
Right, yeah, I mean, even as it is. Well, thanks everyone for coming. I hope you enjoy the rest of the evening. Enjoy the afternoon sessions. Take care. Oh, yeah. Yeah.
With the normal input.
Yeah. the normal. There was one thing. But it was a special workshop for research.
Yeah.
And for multiple simulations. Actually, more, way more. Yeah. No, what I'm saying is that I don't didn't know what to expect. Big problem with lots of people, maybe.
¿Quieres? Yo tengo.
Yo supe cómo le hice. Primero voy clases, todo lo que tenía, a ver el tutorial, no funcionó. Ya, no, después mover los documentos, están ahí. Ya funcionó, pero